Hi, this is Sabrina Glazebrook doing quiz 11. I'm doing questions 2 and 4. So starting with 2. Let f equal 4x, y, z represent a velocity field. Now let S consist of the part of the paraboloid z equals x squared plus y squared within z greater than or less or equal to 9, and the part of the plane z equals 9 that caps off the paraboloid. This makes it a closed surface. Use the divergence theorem to find flux through the surface. So we're going to start by sketching the surface. It's going to be an upward facing paraboloid in the z direction, and it's capped off at around 9. Let's call this 9. At the plane z equals 9. So this is the surface in this vector field. So the divergence theorem states that we take the divergence of that vector field, which is equal to the partial of x of the first component plus the partial of y of the y component plus the partial of z of the z component, which equals 4 plus 1 plus 1. So this is going to be the integrand in our triple integral. So we should now have to find the boundaries over which we're integrating. And we know that we can find that by setting our two z functions equal to each other. But that's pretty straightforward. It's going to be 9 equals x squared plus y squared. So if we were to change this to polar, our radius would be equal to 3. So as we project this surface onto the Rx plane down here, we get a radius of 3. So changing to polar, we can now do our triple integral. Z in this case is going to go from our paraboloid to our plane. So our paraboloid being x squared plus y squared would be just, oops, how do I get rid of that? Sorry. It would just be r squared to 9, and then our r and theta would be from 0 to 3, 0 to 2 pi. And we know our integrand is 6 in this case, so we have 6 dz r dr d theta. Solving for z, we have 6z now from r squared to 9, r dr d theta, and we keep going. Let's start over here. I'm going to put the 6 out front just for ease of visuals. And we have 9 minus r squared r dr d theta. Oops. And we're going to distribute that r into our function. We have 6, 0 to 2 pi, 0 to 3, 9r minus r cubed dr d theta. Now taking the integral with respect to the inner r function, we have our 6 on the outside, 0 to 2 pi, and now we have 9/2 r squared minus 1/4 r to the 4 from 0 to 3 d theta. Putting in our lower and upper boundaries, we get 6 on the outside, 0 to 2 pi, and 81/2 minus 81 over 4, which equals 81 over 4 theta, so we can just simply know that we can just plug in 2 pi, because there's no inner function like cosine or sine to deal with. We're just going to add it to our constant here. So it's going to be 2 pi minus 0 is just 2 pi times our 6 and times our 81 over 4, which equals 243 pi. Is our final answer to finding the flux of this surface over in the velocity field or the vector field given. So moving on to number 4. This one's a little bit harder, but ultimately it comes out to a nice number. So we're going to start with explaining the problem. Find the flux across S, where F is equal to negative z, comma x, comma 3y, and S is the part of the surface, y equals the square root of, oops, I made a mistake there, 9 minus x squared minus z squared. That lies to the left of y equals 2. So we're going to start by sketching the surface. Sorry, am I being loud? I'm sorry. Oops. I'm sorry about this. So we have, let's say, let's call this x, this y, this c, and it's the square root of 9 minus x squared minus z squared, so it's going to start here at 9, and it's only in the positive y area, so it's going to go from 9 to 0. And that's going to reach those. And then we have the plane y equals 2, so let's say that that's around 2, which is going to just cut off this paraboloid at 2. And it also combines at 0. So we pretty much have this little surface to work with. And we'll erase what we don't need. Hey, Luna, get off. And fix that up a little bit. So not really drawn to scale very well, but this is vaguely what we're looking at. And we're going to separate this into 2 different surfaces. So our y equals 2 as our surface 1, and then our y equals the square root as our second surface. Now to find the flux, we're going to have to solve using f dot del g and adding both surface 1 and 2 together to find the flux. So we're going to start with our first surface, which is y equals 2. And in this case, our g function would be y minus 2, setting everything onto one side. Our del g then would be 0, 1, 0. And we can confirm that it's in a positive orientation by just finding or setting it equal to any number on the surface. So say like 0, 0, 1 would be here, or 0, 0, 9 rather, 0, 0, 9. And you can see that it'll still go into the positive direction, or it would go this way rather. Okay, so finding the surface integral of f dot del g over our first surface, we have f of the first surface being our negative z x, and then plugging in y equals 2 into 3y, we get 6. And then our del g of the first surface equal to 0, 1, 0. Finding the dot product, we get 0 plus x plus 0. So we have x as our integrand into our surface integral. So then we can find our bounds of integration by setting, or by plugging in y equals 2 into our surface to find the point at which it's intersected. So we have, it has to be a 2. 2 equals the square root of 9 minus x squared minus z squared. We're going to square both sides. We get 4 equals 9 minus x squared minus z squared. And then we have making everything onto one side, so making the x squared and z squared positive, and then subtracting 4, we get x squared plus z squared equals 5. So in this case, we know that our r, as we'll be changing polar, our r would be the square root of 5. So now that we have everything that we need, we can start solving. In this case, our surface 1 goes from 0 to root 5, 0 to 2 pi. And then our x component here becomes r cosine theta. So we can plug that in. R dr d theta. And we're ready to solve. Now plugging in our upper and lower bounds. Okay, from here we can just put this whole constant out in front and just solve the integral for cosine theta from 0 to 2 pi, which would just be our 5 root 5 over 3 sine theta from 0 to 2 pi. And sine theta, or sine at 2 pi and sine at 0 are both equal to 0, so this is essentially just irrelevant, and making the whole thing 0 for our surface 1. Now we have our second surface, surface 2, which is equal to y equals the square root of 9 minus x squared minus z squared. Now we can find our chi function, which is setting everything onto one side, x, y, and z. And now we'd have y minus our square root, 9 minus x squared minus z squared. And our del g would be, x over the square root of 9 minus x squared minus z squared. Our y would just be 1, and our z component would be z over the square root of 9 minus x squared minus z squared. So we now know our f of surface 2. Plugging in y for the y component would just be negative z, or not y component, but where y is present. We get 3 root 9 minus x squared minus z squared. And we already know our del g, so we can find f dot del g, which comes out to negative minus z squared plus x times 1 is x plus in these components the square root cancel out, so we just get 3z, and this would be our integrand to our surface integral. So we're pretty much ready to go. Oh, and we should know the bounds too. So in this case, you would go from our square root 5 that we found previously to we just have y equals square root 9 minus x squared minus minus z squared. Squaring both sides, we get y squared equals x squared minus c squared plus 9, and then we can put these onto the other side. So we get a sphere, x squared plus z squared plus y squared equals 9, and taking the square root of that, we get r equal to 3. So we know that our bounds would go from root 5 to 3. So our surface integral would then be from 0 to 2 pi root 5 to 3. And then in this case, equal to, here we'll write it out. X would be equal to our cosine theta, because we're changing to polar. Our z would be our sine theta, and then our y would be root 9 minus x squared minus y squared, which is essentially 9 minus r squared. So, given all that, we can write out our integral, which would be negative r squared cosine theta sine theta over root 9 minus r squared minus r cosine theta plus 3r sine theta r dr d theta. And I'm going to jump to the next page for some room here. So we can start solving the first one. I'm going to start by just plugging in r into the inner function. And then I guess we can, we shouldn't start with that. Negative r cubed, or we can actually write this as r times r squared. It'll be easier to visualize when we do u sub. Sorry, my cat is in the way. I can't write. Okay, so we're going to separate this into chunks. The first one mostly just needed some extra room, but the other two are easier. But for the first one, we're going to use u sub, and u in this case would be 9 minus r squared. Our du would then be negative 2r, and we can also use r again in this case because r squared is equal to 9 minus u. So then we would get the following from, it would be our 9 minus u over root u, and we can't forget our negative 2, or our 2 rather, so we'd have to put half on the outside, du. And we can also change our limits of integration, r and u. So r, instead of going from root 5 to 3, it now goes from 4 to 0. And this one's pretty straightforward. It would just be 1/3 r cubed cosine theta. If we were to solve that, just r, we would have 1/3 r cubed from root 5 to 3, which is equal to 9 minus 5 root 5 over 3. Can't forget the cosine, we'll put that in later. And then we have our final one, which is r cubed sine theta. And so our r cubed from root 5 to 3 be equal to 27 minus 5 root 5. So I'm actually just going to put sine theta out here, cosine theta, so I don't forget. So, given all of that, we can integral, our first part of the integral, by putting setting u equal to negative 1/2 and solving it like that. U times u to the 1/2 and distribute, which would be equal to, I almost forgot to put the other one in there, 2 theta. I almost forgot the cosine. So, after distributing, we get okay, and we should start plugging in our other two just so we don't forget about them, which is negative 9 sine theta minus 27 cosine theta minus 5 root 5 over 3 sine theta plus 5 root 5 cosine theta from 0 to 2 pi. So, I'll keep going. Expanding our first part, we have 0 to 2 pi, 1/2. We get 0 minus 0 minus 4 to the 1/2 is 2, 4 to the 1/2 is 2 times 18 is 32, minus 4 to the 3 over 2 is 8 times 2 is 16 over 3, 16 thirds. And we have our sine theta, cosine theta, d theta, minus, and if we finish off our last two parts, we have Sine at 2 pi is 0, minus cosine at 2 pi is 1, so we'd have 27 minus 0, plus our cosine again would be 5 root 5, and then we plug in our 0, we get 0 minus, and it would just be the same thing for cosine as well.
Taking a final?
I'm not taking the final, recording a quiz. So essentially all of these would just cancel out and we would get 0 for our second part of the integrand. So now we're just left with the first one, because all of this cancels. So this comes out to be 0 to 2 pi. I'm just going to clean it up. It ends up being negative 56 over 3 sine theta cosine theta d theta, with some simple u equal to sine theta, du equal to cosine theta. Changing our limits of integration, we have, instead of from 0 to 2 pi, we get 0 to 0, which makes this all very much easier. We have negative 56 over 6 u squared from 0 to 0, which is just 0. So 1, which is equal to 0, plus our surface 2 equals 0. Our flux ends up being just 0. Okay, thank you.